Great, so we are now live. So thank you all for joining for this new reading group session of ContinualAI. Today we have the pleasure to host Min Lin that is going to talk about continual learning from the perspective of compression. So thank you so much, Min, for being here with us today, and the stage is yours.
Thanks, Vincenzo. Thanks everybody for having me here. So today I'm going to talk about the workshop paper on continual learning from the perspective of compression. So this is a work done jointly with Xu He from University of Groningen. And in this paper, we are, how do I, do you know how to turn the page with the arrow key?
Can't you do it with your keyboard?
I got it.
Okay, cool.
Okay, great.
Sorry. So first, in continual learning, we are trying to make predictions on a sequence to learn from and make predictions on a sequence of data. So we denote as xn, which is a set which contains x1 to xn. It's a sequence of data. And in compression, we can write the description length of this sequence as two terms. And the first term means given a model theta, what is the length of the data under this model? Another term is the length of the model itself. And of course, there are other ways for compressing. This is not the only way. There are other coding methods that is only one part code that doesn't concern the model length, and we will see it later. So to compute the first part of the length, we use the idealized Shannon-Fano code, because here we are only analyzing the length of the data, but not really encoding it. So the idealized Shannon-Fano code is written as the negative log probability of the data under the model. So here the model is a generative model, like a VAE. Maybe not GAN, because it doesn't have an explicit likelihood. And we can have a VAE or normalizing flow or other models that has an explicit likelihood. Okay, so to compute the second part, which is the model length, so we need to introduce the concept of Bayesian mixture code. So in Bayesian mixture code, we have a prior p theta over the generative model parameters. And this is usually fixed. For example, a standard Gaussian distribution. And we sample a model from this prior and use the model to encode the data. And then we sample many of them and take an average. That's why it's called Bayesian mixture, because the models are sampled from this prior and mixed. So there's a lower bound to this mixture code, which is the famous elbow. And the elbow contains two terms. The first term is we sample the model from the posterior Q, and then try to encode the data under this posterior. And the second term is the KL divergence between the posterior and prior. And if we use bitspec coding, this KL term represents the length of the model. And there's another type of code which is called Prequential Code. So the Prequential Code treats the coding problem as a prediction problem. So we always try to predict the last data that comes in time, given all the previous data. And then we do this recursively. Then we can encode the entire sequence. And the core of the Prequential Code is the prediction strategy, which is given previous data, what is the likelihood of the next data? And there's no explicit model description as required in the Prequential Code. So Bayesian mixture code, as we introduced in the previous slide, is a Prequential Code itself, because we are predicting the next data point xt by sampling from a posterior distribution given all the previous data. Its prediction strategy is like this. And there's another code called maximum likelihood plug-in code, which is also a Prequential code. So in maximum likelihood plug-in code, we are trying to fit a parameter theta using all the previous data. And I use this model to make prediction on the next data point. So the theta given all the previous data is argmax over the log probability of the previous data. So it's a maximum likelihood model. And we get the parameter, try to predict the next data. And this is also called further leader in online learning literature. And so at this point, we can have an information theoretic definition of forgetting. So let's think of a generative model. When we try to do generative modeling, if the data is streamed online and we are trying to add the data one at a time to the generative model, then since we discard all the old data, so we have lost the information of the data itself, but all we have is the model, right? So in this case, all we have is the L theta term here, which is the model. And we don't actually encode the data under the model and store the code, right? So we lose the first term, but we have the second term, which is the generative model. So the information we have lost, we can define it as forgetting. So when we try to update parameter from theta I to theta j, we can measure the difference on the first term by subtracting the code length on two different parameters. And then here the max over this difference n0 is to prevent negative forgetting. We only have defined forgetting as the increase of lost information. Okay, so with this compression framework, we can put the two paradigms of continual learning under this framework. So we know that there are approximately 3 paradigms in continual learning. One is called variational continual learning, or they have some other names like regularization-based methods. So under this variational, so by abusing the variational continual learning term, I'm not referring to the paper, which is called variational continual learning, but referring to the family of methods that use a Bayesian prior and continuously update that prior. And under this family, they are the EWC, synaptic intelligence, Riemannian walk, etc. And there's another family which I again abuse the term, put it under the deep generative replay. So basically, in this family, we are storing the data in a generative model or in a replay buffer and try to recall the previous data and retrain it on our model. So these two families, they can be united under the Prequential coding framework, where the variational continual learning is equal to the Bayesian mixture code, and deep generative replay is equal to the maximum likelihood plug-in code. And I will show you why they can be put it this way. So first, for the Bayesian mixture code, as we have seen from the previous slide, the prediction strategy of Bayesian mixture code is to predict next data given all previous data using this strategy. The strategy is to sample from the posterior of theta given all previous data and use this model to make a prediction on the new data. And we sample a lot from the posterior and take the mixture, the integration here. So in VCL, this posterior is approximated with a variational function Q of theta. And since there's a relationship between the posterior and a recursive relationship between the posterior at time t and the posterior at time t minus 1. So we can derive a recursive update rule here where the approximates distribution Q can be updated recursively. Given the previous time step, we can compute the new Qt. Okay, so the next is the relationship between deep generative replay and maximum likelihood plug-in code. So this is quite straightforward because in the ML plug-in code, we fit the model on the previous data and use it to predict the next upcoming data. And we can also form a recursive relationship between the maximum likelihood on time t and maximum likelihood on time t minus 1. So basically, we can decompose it into the likelihood of the current observation and all the previous observations. Right? But since we don't have the old data, so we cannot compute this term exactly. And we actually use the data that is stored in the generative model. So, okay, so the first line here shows the exact likelihood, which is dependent on all the previous data from I to t minus 1. And the second line is the approximation, which we replace the real data with the data sampled from the previous model, theta t minus 1. Okay. And we can recursively update theta t in this way. Okay. And we know that from the literature, there's a paper called Towards Robust Evaluation of Continual Learning. We know that usually VCL or variational continual learning approaches doesn't work very well in practice without a cause set. And actually, according to that analysis paper, if you add the variational continual learning part on top of the cause set, it's only improving marginally on the permuted MNIST, and on split MNIST is almost equal, so it's actually not working. And we try to test this in terms of generative model, in terms of compression. And the first graph shows the bits per dimension of the data as we try to, the first figure measures the forgetting through time, measured in bits per dimension. And we can see that the catastrophic baseline is the most severe in forgetting. And VCL is forgetting only slightly less than catastrophic. And the maximum likelihood mixture is much better. And ML plugin is even better because maximum likelihood mixture can be I haven't introduced. I haven't introduced maximum likelihood mixture. Actually, we are in this figure, we are going to compare the VCL with Bayesian mixture, because we can see VCL as an approximate version of the Bayesian mixture code, and see replay as the approximate version of the ML plug-in code. So we can see that the Bayesian mixture is actually quite good, but after doing the VCL approximation, which replaced the real posterior with the approximate posterior Q, it's forgetting much more. And the same trend can be also seen in the measure on the code length throughout the time. And we can see that VCL has the longest coding length here. So, okay, so we know that the deep generative replay, it has good performance, and it performs in raw input space, which we sample from the input space and try to replay it. But we don't want this feature, because when we try to replay in the raw space, it is uncompressed. We store all the previous data, and it is computationally and memory inefficient. And VCL is good because it's in the parameter space. It is a KL regularization. And if the KL is something like Gaussian, it's very cheap to compute. And we can think of the parameter space as a compressed space. We usually will interpret when we optimize a neural network with the raw data we have, what we get in the parameter is something more compressed than the data. But in practice, VCL has poor performance. So from this, we will say, okay, we would like maximum likelihood plug-in code, which is the replay method, rather than the Bayesian mixture code, which is the VCL method, because usually the replay is better than the VCL approach. And on the other hand, we want to make it in the parameter space than in the raw input space because of the advantage in the parameter space. So can we have both of these properties to have a maximum likelihood code in the parameter space? And the answer is yes. So we can merge these two strategies. So this is the ML plug-in code prediction strategy, and this is Bayesian mixture code strategy. So we can arrive at maximum likelihood mixture code. And we can derive a lower bound to this maximum likelihood mixture method. And I'm not going into the details of this, but I will tell you an intuition of this method in the coming slides. Okay, so this method is also composed of two terms. The first term is the likelihood, the elbow of the current data, plus another term, which is the KL to prevent forgetting, by comparing the current prior distribution and the previous prior distribution. Okay, and it also forms a recursive updating rule. So computation-wise, it is similar to the VCL approach, and it is also less demanding on the prior distribution. And I will show why. And there's less forgetting and better compression compared to VCL and Gaussian. VCL with Gaussian prior. And you can see here the ML mixture is a purple curve, which is worse than the replay method because it's a regularization method, but it's much better than the VCL. Okay, so first, intuitively, what is in VCL is that we try to map, we try to have a generative model by mapping the latent space Z. Let's say we have a Gaussian distribution in the latent space, like a GAN. So we try to map the Gaussian noise to the data space through some decoder, which is parameterized by theta. And in VCL, we try to model the parameter itself as a distribution, which is modeled by the hyperparameter phi. But in ML mixture, we actually, so imagine we take a decoder and we take all the parameter of the decoder and concatenate all the parameters with the latent code Z. And then we treat it as a new latent code and try to map it to the data space. So in this case, the mapping has no parameter at all. It's just the backbone of the neural net. Is there any problem with this interpretation? Okay, so we have, in this way, we can have a one-to-one mapping between the latent space and data space. So for every data X, we can find a posterior distribution in the parameter space. Okay. And to achieve continual learning, all we need to do is just, for the incoming data, we find the posterior distribution in the parameter space. And for each of the data, we have such a distribution, and then we keep the mixture of all this posterior distribution, then we are not forgetting. So, so here, on the left-hand side is the data space, right-hand side is the parameter space. So in VCL, we usually will say, okay, with data A, we have this region in parameter space that could explain data A. And for data B, we have the other region that explains data B. And then if we are learning continually, we are going to take the intersection between these two data. And this figure is often shown in the regularization-based methods papers. But this is only optimistic, the optimistic case where the distribution in the parameter space for both A and B is kind of Gaussian, and then you can get a Gaussian with the intersection too. But in the realistic case, it could have a very structured distribution in the parameter space. And then you have a multi-mode distribution, which cannot be easily captured by a Gaussian distribution. So if we are trying to use a Gaussian to fit the intersection of A and B in the parameter space, then when there's a C coming in, and if your posterior is only capturing this mode, and then the C is going to intersect with this mode, then you are not going to be able to learn continually anymore. Okay, but
Min, is this in the paper? These little figures and the explanation?
Nope.
Okay. Because I was trying to articulate this in my pre-doc, and I got so much pushback on it. But if at some point there was a document I could refer to with these explanations, it would be nice. But I guess it's hard to formalize this. But yeah, anyway.
So the idea is the real posterior of the parameter given all the data is super complex, and it cannot be captured by a Gaussian. So if we try to fit with the Gaussian, it's likely only capture one of the mode and then use most of the information. Then we cannot learn continually without forgetting.
Yeah.
Capturing this complex structure in the parameter space is way too hard because the parameter space is huge, and the generative models, if we are trying to adapt it to the parameter space, is going to be unacceptable. And also another problem with this is if we use a compressed model to force capture this compressed distribution, then we don't have an analytical form when we calculate the KL divergence. We have to do Monte Carlo. Then doing Monte Carlo is inefficient itself. Then why not we do Monte Carlo in the input space by replaying it, right? Okay. So the ML mixture has a different paradigm because so think of the decoder view that I introduced earlier, where each data point can be mapped into the latent space. So A mapped to the region A in the theta space. Here, theta including both the parameter and the latent code of the decoder. Okay, and A and B, they are going to be disjoint sets because it's a decoder. So in this case, we don't need to capture the entire distribution, but we can just take a Gaussian at the intersection point. As long as this Gaussian covers both region A and region B, then if we sample from this Gaussian and push it through the backbone of the decoder, we will be able to generate both A and B. So that's why, in this case, it's easier to capture both the data using some simple distribution like a Gaussian, because we don't need to capture the entire posterior. Okay, there comes the summary. So in this work, first we propose a information theoretic definition of forgetting, and then under this definition, we can unify the VCL and deep generative replay families under the Prequential coding framework. And then we analyze the limitations of VCL. This is not presented here, but it's in our paper. And we introduce a new continual learning scheme, which is called the maximum likelihood mixture. And yeah, thanks.
Thank you so much, Min.
Thanks, Min,
for your very interesting presentation. So do we have any question for Min?
Maybe I have one. So do you think that we should use this continual learning compression scheme as like a new benchmark in continual learning, or?
So I'm not okay. So I think in the generative model case, if we are trying to do continual generative modeling, it is good to measure the compression rate, which is actually the likelihood.
Yeah.
I'm just putting all the previous method under the Prequential coding framework. So there's nothing new about the equations or formulations here. And yes, I would say for the generative modeling, we are going to, it's good to evaluate the description length. And also for the discriminative models, it actually can be reformulated as a generative model because we can model the joint distribution, right, of the input and the label.
Yeah, that's right.
And also, there's a recent paper, ICML, saying that if we are going to do optimal continual learning, we need to store all the information.
Yeah,
all the
and it's NPR'd.
Yeah, and so I think it makes more sense to measure how much information we are actually capturing in our model.
I see. Yeah, maybe actually that paper would. Oh,
go ahead, Massimo. Go ahead.
I was just going to say maybe at some point we should get that author to talk about this paper because it has a catchy title.
What was the paper again?
I think it's called Optimal Continual Learning. It requires infinite memory and is NP hard.
I think one of the authors is Tom Diate that we had already, I think.
Damn it.
Groups.
Okay,
so
yeah.
we know him.
I see. I missed that one, I guess.
But we can contact them again, I guess, because it's true that it was a an interesting paper. I haven't read it too, but it would be nice to hear from them. So, Min, do you have any ideas on how to push this work forward, or not yet?
Right. So there are a few difficulties here because so as you see here, we are trying to use a very simple distribution to capture all the data points. So the problem is if we initially have data A and B, and then we fit it with a simple Gaussian, which is good, and then we introduce the third data point, is the feasible set of the third data point going to be near this region or not? If it is not near this region, then we cannot expand locally to include the third data point. So for now, it's from our experiment results, it seems that it's fitting good initially with, let's say, for example, the incremental MNIST with 0, 1, 2, 3, 4. And it's fitting good on 0, and then it's going to capture information of 1, 2. And then as it progresses, it's going to capture less and less information because it has been stuck in the local from the beginning. So it has the opposite behavior of VCL. It's not forgetting at all, and it's not learning. It's not learning much. It's learning a bit, and its capacity depletes quite quickly, and we are still trying to figure out how to overcome this problem. But yeah, overall, this you can think of it as continual density estimation, so which has explored quite a lot in the literature. And I think it's quite general because the discriminative model can also be reformulated as a density estimation problem.
Thank you, Min. Do you have any more questions?
I guess maybe I have a last question. I'm sorry if I missed it, but in your baselines, is there like a method that will spawn different models per task and then just choose whichever model it should use for the current data given their likelihood, maybe?
No, there's no such design.
Okay.
It's all shared.
I see. Because essentially that solves the problems. I mean, if you can do correct task inference, and if you only focus on forgetting, then you could solve the problem with this kind of mechanism, right?
Yeah.
Because you don't need to learn models at the intersection of both density functions. You can just have one per.
Oh yeah, I see what you mean. So basically, if you treat A as a data set and B as another data set, then you can just learn a Gaussian for A and another Gaussian for B, and then we just use the Gaussian mixture.
No, but it's still, I mean, if you're trying to predict the likelihood on a given data point, you still need to choose a model somewhere. And so the task, so I guess I call this task inference, and you still need to solve that problem, and you're still gonna get forgetting in task inference, maybe, I don't know. But essentially, if you can get task inference right, then you don't have any forgetting. Right?
Yeah, I think so.
Yeah, I guess I'm just I'm wondering how it would compare to the other.
Yeah, I think there's a link here because what you said as the task inference, you can think of it. So in the generative case, you can think of as the Bayesian mixture code, where you are trying to encode your data with a bunch of models. There's a mixture of this model. You take the integration over these models. And since there's a lower bound to the Bayesian mixture code, right, which is infer the model, use a model to encode your data, right? And another term is how many models do you have? If you have 100 models, then selecting one out of it is going to cost 1/100. The bits, which is with the probability 1/100.
I see.
Mm-hmm.
Yeah.
Okay. Any more questions? All right. So I guess thank you, Min, for your time, for your presentation. And I invite you, if you can, to share the slides on our forum where I created a topic which we can continue this discussion. And I invite all the other people who are here today to join our next reading group session, which is going to be next Friday. So thank you again for all of you for joining, and see you then. Bye.
Thank you.
Thanks, man. Thanks, Vincenzo.